Yeah, topic of our conversation today is Core ML Vision Framework. And let's start with agenda. We will begin from the introducing ourselves, and as it is one-side communication, so I will be talking just about myself a bit, just for you to know me better. Then there will be a theoretical part, more about what is computer vision in general, what applications it has we can use, and we'll have a couple of words about Core ML Vision Framework, and then we will move to the practical part, where I will show you how to create a custom Core ML model, how to train it, and indeed what wolf pits you can omit on this way. So without further ado, let's move forward. So who I am? As already been told, I'm a public speaker in terms of sharing my knowledge with others. I do work in Sweetless Systems as a team lead and lead software engineer. And thus, I have a lot of opportunities to investigate in new technologies and to work with them. And I like to share this knowledge with others because I think when you do not share, the knowledge is just dying out. I have adjusted to public speaking from the very childhood. I like this thing, and I think it's useful for everybody when you engage in a lot of smart people to do smart stuff. I also like tabletop games and like to watch movies, Marvel Universe especially, yeah. And I also participate in the intellectual games. Also, I have a lot of friends whom I engage in my preparation to my speeches, and this is gang who prepared this particular one. So you can say I'm this kind of a geek. Let's move forward to our topic, computer vision. Computer vision, by definition, is transforming visual information to the information itself. So it's extracting information from the images. Basically, when you have a drawing of a shark, the computer cannot understand this is the shark by itself. You need to extract this information from the image. So as I mentioned, you're transforming images into the words, into the information, which can be later reproduced, and later you can work with it using other algorithms. So what are applications of the computer vision as a tool for transformation visual information? We have, and we know, a couple of them. First of all, image identification. What is this Pokemon? Yeah, what we can see on the image. It's a generic classification task. You can apply and get the information what is on that image. You can sort images, group images by the topic, and so on and so on. Controlling processes. So on different manufacturing, yeah, you have stages of the manufacturing the thing. For example, assembling or disassembling Iron Man suit. And you want to know on which specific step you are and whether it was completed perfectly. Yeah, if to move from the fantastic examples, let's to the real life examples. For example, once again, manufacturing of the car. It has multiple stages and it almost fully automated. And you want to know whether the engine is ready to connect to the transmission and so on. Detecting events. So it's usually applied to video streams. You want to see not only the stream itself, but for computer to understand whether it's something going on there. For example, yeah, Captain America overrunning his friend. And real life example in CCTV, it's usually identifying whether some criminal activity is going on. So detecting events on the video streams, one more application. And interaction. Yeah, computer vision can be used to interact with the human as an interface. For example, Kinect. Yeah, we can see on this picture how two fellows interacting with the Kinect and playing the video game, Dance Dance Revolution, I would say. So it's not also a tool of identification what is going on, but you can like use it as an input tool. Navigation. Popular right now with the Tesla cars and other automotive vehicles, maybe ships, aircrafts, and so on and so on. So you want to navigate by visual information. Yeah, a lot of companies works with the automotive navigation, but if to highlight, aviation navigation also uses visual viewpoints to navigate aircraft. Basically, the whole aerospace is divided on viewpoints from which to which aircrafts are flying. And automatic control of these viewpoints and identifying them is also important tool for the aircraft navigation. Medicine. Yeah, in particular diagnostics. Computer vision helped to do a lot of breakthroughs. For example, identifying the cancer markers. There was a study which compared how good is computer vision comparing to trained doctor vision, yeah, and identification of the cancer markers, and it get funny results. Computer vision did like 93 or 94% precision, and a human trained doctor around something like that, 92, 93% of precision. But when you combine those two approaches, it happened to be synergized, and doctor vision and computer vision together increased success rate to 97%. How it works? Yeah, computer vision is better in identifying the correct results, correct markers, and human vision is better in identifying wrong results. So basically, one approach helps another to evolve. And that's a great example how computer vision and human eye can cooperate. One more application is machine vision. We have a lot of automation tools and we have a lot of robotic, but fully automated, it can be only when it has a vision. For example, harvesting apples. Yeah, you need to identify whether apple is ready to be harvested, where to put it, how to how to harvest it without harming the tree, and so on and so on. So computer vision gives machines ability to be really independent, to work properly and automated. Also, as most of the technological and scientific achievements, we cannot omit military applications, and it's mostly navigation, as it was mentioned previously, but also image identifications, and so on and so on and so on. So military uses the computer vision in its power. And we know as scientists that military budgets usually pretty big, so you can understand that involving good finances allows to develop this field as well. And autonomous vehicles. Yeah, this is the separate topic as we are, as a humanity trying to move ourselves to other planets, we need to investigate them upfront because we're not able to travel too far for now, but we enabled our inventions to travel far ahead of our planet itself. So, for example, this is Perseverance, and it's currently on the Mars in the search for the evidence of life there. It's the main mission, but as you probably know, there is a big time gap in transferring signal from Earth to Mars, and you cannot drive a vehicle with a long minutes delay. Yeah, so you need to enable it to be able to move by itself, and computer vision allows it. Obviously, if it stucks forever. So you need to be really, really careful and really precise. That's why these autonomous vehicles move very, very slowly. And there are many, many more examples of computer vision. And final one I want to give it to you is how the computer vision models can be trained by engaging ordinary people. So you don't have to be data scientist or something like that to help to develop our future using computer vision. This is the screenshot from game EVE Online, and they've embedded a miniature game inside it. So while you are flying through the galaxy, you have a lot of time, idle time when your ship just flying automatically. And players can participate in small games. It's called Project Discovery. And this is a screenshot from 7 or 5 years ago, when the Project Discovery was about exactly identifying the cancer markers in the cell samples. So what you have to do, first you were on first ranks, you were identifying the simplest samples, and you just trained yourself how to find out whether there were or wasn't the cancer marker. And then later, or in some random moment, you were given a sample which was not previously identified, and if you have a high success rate, and you help to train the model how to identify those cancer markers. And that's just a game. So a couple of years ago, they changed this project to the exoplanets research. So you were provided with the samples of the solar signals from the different stars, and they might be obscured by their planets. So the signals obscured by the planets, and you need to identify whether this gap in a signal is just some error, or probably maybe an exoplanet which can be terraformed and human can travel there, live there. So as just a gamer, you can help to develop the science. And we're moving forward to Vision Framework. CoreML Vision Framework is an Apple framework which allows you to do a lot of this stuff just by using your device and on device, and embed this functionality into your application. Let me share my screen once again to show you how it is look like in Apple side. So yeah, it has the pretty good documentation, pretty detailed, and it has a lot of functionality you can apply as the programmer. As you can see, so it can analyze image sequences and still images, detecting and tracking object on a video stream, face and body detections, and many, many more things. So I highly recommend you to view this documentation page to see what you can do with this Apple framework. And we will move forward to some examples. So let's try to create CoreML model. To do that, we need just to type create ML. This is the application of which delivered with an Xcode, and you create your own detector. I've already prepared the one for you. Yeah. Let me reshare my screen. Just entire screen. Yeah, great. So now you probably can see my screen. So yeah, you create a new project, yeah, and there you select what you are trying to detect. In our example, we will try to identify the side of dice, yeah, six-sided dice, which side it's up. So when you create a project, you need to select what you're going to do. There are a lot of groups, so image, video, motion, sound, text, and table, and we're interested currently in image. Object detection, and you create a project, authorize it, license, and get a description. As I mentioned, we already have the sample project, and let's see what we have here. So in order to train a model, you need to specify a data, yeah, what you will use for your detector. I have already prepared the data. We can view it. Yeah, it lies in the folder. Let's open it. Okay, I've renamed folder for this particular session. It should be like that. Let's check. Space. Okay. Okay. Yeah, here it is. So now you can see the training data. And let's view it once again here. Okay. So we have our object detector, and we have a lot of options. First of all, you can select the algorithm. Let's add the new one for the sake of simplicity. So there are two options for specifically for image detection and for the object detection on the image. You can use the full network. It will be training from the very beginning, and it takes a lot of time. But there is another option to use transfer learning. And what does it mean? It means that you will reuse the already trained network from Apple, which basically they're using in their photo application and so on and so on. So for our example, let's use transfer learning because we're trying to identify the object that already known. If you use full network, what happens? Just for example, it automatically sets number of iterations. the number of iterations can be changed based on the training data. For example, if we select our training data, which have 6 classes and 45 items, we can, it's not showing it for now, but when we will start training, it will work. 6 classes because 6 sides of the dices and 45 images. And full network algorithm suggests us to use 5,000 iterations. If we move to transfer learning, it also suggests 5,000. If you change the number of items to bigger one, it will definitely allows you to lower, or it will suggest lower number of the iterations. Definitely you can change it by yourself. If to come back to the full network algorithm, it has batch size, which is auto. Yeah, it means how many items you will use in each iteration, and it's suggested to keep it auto. And it has a grid size. When you train a full network, it splits the image you annotated and suggested to be on a grid. And grid size is 13 by 13. For example, if an image, if the grid cell does not contain the interesting information, it will be skipped. But if it has a drawbacks, if it has a partial image or partial image of our dice, for example, then it can be missed as well. So we will use transfer learning, which do not have this option. And as you see, this is the project settings. And what you can do, you can tap train, start training, and it will move to another tab. It has number on the right-hand panel. Yeah, we can see number of iterations, we can see data set, and here we started a training itself. I want to highlight that this is the training of your model is the highly time and resource consuming operation. So in this case, you need to prepare yourself that it will occupy a lot of resources on your laptop or computer, anywhere you're working, and you will not be able to do everything, like something in parallel properly. So what I did, I've left my laptop to work overnight in order to train the model previously. And as you can see, while we are speaking, the training process is going on. It's on iteration 12 already, and it decreases the loss dramatically. At some point, you will see that the loss is around, like, pretty small number, around 0. And you can pause the training at this point because it will not get better. So, but on the other hand, if your training loss does not decrease as dramatically as you want, you can also, the training process will stop on number of iterations. For example, you set it to 1000, yeah? And you see that result is not good enough. You can proceed training on this very same model by adding the number of iterations. It's also possible, and you can do it. Anyway, so while we are training our model as an example on a background, I want to highlight a couple more things. First of all, it's all sounds simple, yeah, and you will see, and I will share with you at the end of the session, I will share with you links to Apple videos they provide, and you will see it's all perfect. It works like a charm and gets no problem. But as you understand, in real life, it differs. For me, and from my experience, the most challenging part was to prepare the data. In order to upload this training data, you need to mark it, you need to annotate it at first. So let me give you an example how it was done for the current session. So let me just run the application on the background for you just to view the, yeah. So, okay. Let's see. So training data is basically a set of images along with annotations JSON. We can see, let's look at it. Yeah, so it's pretty simple. It's what, as I mentioned, it's JSON. It has image with its name and annotations to it. As I mentioned, it annotates the dices and it labels number of the dice which is displayed, number of pips on the dice. Let's see an image, for example. Yeah, so 1, 6, 4, 3, 2, and 5. Yeah, and in annotations JSON, you see the same labels. So each image contains photo of 6 dices, which each dice is on a different side, and it has coordinates x, y, width and height, which represents the square area where you can see the information we're interested in, labeled information. And yeah, first thing you need to remember while annotating the images that the Apple uses XY coordinate system, but which starts in the top left corner, not like we learned on the lessons on the bottom left corner. It starts on the top left corner. So you need to consider this while providing the coordinates. And as you can see, for 45 images, which is our data set, it takes pretty long time. You can imagine it takes pretty long time to annotate. So what you can do, from my experience, you need to automate everything you can. And in order to do that, me together with my friends, we created a script on the Python. Yeah, this one. Okay, don't save. Okay. Let's try. To automate everything you can. Once again, you can use scripts and you can use other tools. So as for other tool, I've tried Roboflow, which is just one that I Googled. Yes, and it allows you to upload images and create your own data sets Let's see. We have already annotated and uploaded image sets. So what you are doing here, you are selecting area of the dice, yeah, where you can see the interesting information, interesting for you. And you can label it with any label you want. So as I mentioned, on each area, I've selected the dice side with the useful information. I've tried to select only the the side where you can see correct number of pips in order not to like mislead the neural network with the additional information. But it, as you will see as a result, it didn't help a lot on such small number of trained objects, of trained items. And you can upload images, you can select them from the from this tool, yeah, and you can download the image set with annotations JSON from this Roboflow. But you need to consider these things. First of all, whether you need to pay or you need to create public or free project. That is because you cannot upload everything, yeah, without subscription, or you need to make it public. One other great example is when you, for example, when you do mistakes, yeah, maybe write your algorithm incorrectly, you can check the results using images. So, yeah, you see that was the first run of our algorithm, which placed or marked the dices incorrectly. So everything is there, but scaling factor was wrong. And as you saw here on the JSON, yeah, you cannot like read it from the document itself. You need to let me move this project folder for now. You need to somehow visualize it, and you need to find the tool for that, because you will not just understand. Okay, let's try a script. So core ML and script. Okay. So we have a Python script, which what it do? It gets the data from data folder and create annotations JSON in output folder. And it uses OpenCV as the tool. And what it does, it's finding the white zones. Yeah, that's why we use white dices on the contrast background. It finds the white zones on the image and look for dark zones inside of the image and counts them. That's it. So basically you look for a white zone and look for the dark zones inside of the white zone and count them. When you count them, you will get the number of pips, and you can mark this white zone with the square area as a dice. So let's try to run it. Yeah, we need run main py. Okay. and what we get. So we have this white image, yeah, which identifies white zones on the image, and there are smaller images which identifies black zones, black dots inside of these white areas. And yeah, as I mentioned, we have all sides on one image, and going through the images, all images in the folder, it creates the resulting annotations JSON. But as I mentioned, even automating the marking of your data will not make it perfect and will need adjustments. So let me show you in the folders. Okay, so it was data here, and in output we have annotations. And now we need to somehow verify whether these annotations were correct. In order to do that, we have another script which called view annotations, and let's run it. And it works in a matter. It collects the data from annotations, JSON parses it, gets the image name and marks the image with those areas, square areas, labels it accordingly, yeah, and gives a number. It's not really good to see it, but it has the number in the array. So we have, for each image, we have an array. Yeah, and order in this array is numbered here. And you can verify whether your data was correct. So it seems like on this image works, everything works perfectly. On this also good one. Yeah, but from time to time, we will see incorrect markings, and even, yeah, let's move forward. Even that we do not have identification of number of pips at all. So far, so good. Yeah. So for example, yeah, this one. We have known result. Obviously, it's not a good data. So you need to go to the to this annotations JSON, yeah, and look for the image. It will be 1362, and look for the incorrect label. So it's known, yeah. Obviously, visually, you can confirm that it should be 2. You just correct it and save. And in this method, you can go through all of the images and create a correct one. And then when you have a correct data, verified correct data, you can move forward to feeding this data to the model. And then it will go as simple as I shown to you. So let's see. Let's go back to our object detector. As you can see, it's still training, but as I said, even on iteration 167, it's already trained good enough, and you can stop or pause the result. At any moment, you can create a snapshot. which is basically the trained model at that point. So let's move forward. As you can see on this example that I did previously, we've used the only 1,000 of iterations, yeah, and it's already resulted somewhere on first 200, yeah. And what you can do, you can evaluate your model, yeah. You even can add, so let's move back to evaluating. Yeah, you can add testing data, yeah, and validation data as a data sets from the very beginning, yeah. You can select another data set, but it also need to be marked in order to model to self-validate. And same way here, you need to add data to test. But even more, you can preview the results of the trained model on some image. So I have folder with not to process images, and yeah, let's pick a random image and add it here. So now model is trained model, yeah, trying to identify things. So for this one is 100% of confidence. It's 4 definitely, and it works fine. For this one is 88% of confidence, and that is also fine. But here on the dice, where you can see like a bit of side, it's not so confident. It see at least it's confident for 92%, but it's confident that this is number 2 because it sees 1 and it sees second from the side. We can select another area. I can like tap on it directly, unfortunately, but there is another square inside of this blue one, which says that, yeah, here it is. I was able to select it. That is 100% number 1. So the problem is here that if you see or if you provide the images, yeah, which is not like directly over the, for example, over the dice, it can be misleading to the model. How to fix it? First of all, you need better to select areas. You need to provide more images, and you need to provide more images under the different angles. Then model will be trained properly and will identify the images more properly and dices more properly. But nevertheless, it has correct results, as you can see. Yeah, this is correct result. Let's see. This thinks that it's 4, yeah, and this square thinks that it's 2. Not correct result. But here we can see better results, and when there are multiple dices within areas really close to each other, it can also be misleading. So Core ML or Create Model gives you a lot of tools how to train your model, how to validate the results, and how to select the data and how to select the images for validation, and so on and so on. Minimum requirements for training object model is like to have around 50 items, at least 50 items. I specifically added 45 in order to show you where it fails. And all of them should be marked. So let's see what we can have in the result. I've selected this example by the multiple reasons. First one is that I like tabletop games, and second one, Apple already created the sample application, yeah, with which detects the dice sides on the screen, and we're using it to review our model. So on the right hand of the screen, you can see the feed from the iPhone. Yeah, so let me correct it a bit. This is the area I photographed, and here we have dices. As you can see, it uses the model. Let me move all them a bit closer in the screen area. Yeah, it uses the model to identify the images. So images were taken under the, now it uses the Apple model, not our model. But the lighting can change this result dramatically. Let me enable the lighting and change the brightness and maybe a bit change the angle. So what it can see, yeah, it can see some of them, but as you see, a lot of issues with the identifying of the dices appears. So training model is not so simple, and you can like have a lot of invalid results, but you can work with that as well. So we can change some additional values in the application itself. Let's change the threshold for confidence, and we'll see what it will give us. Let's have it 2, and let's have confidence threshold to 1, 0.1. Replace. Give it a time to rebuild. And let's see what's changed. So yeah, once again, let's try to give it closer. Yeah, it has slightly better results, but not perfect as well. But from time to time, oh, okay. So now you can see that its confidence changed, and now it can see 6 instead of 3, where it previously saw 3, and so on. Let's tweak it a bit more. Let's give it 1 and 0.2. Replace. And now, yeah, it definitely sees 6. It definitely sees 2. Here it's 1. Also changing the results without additional lighting. Okay, let's increase the light and let's decrease. So you can see that you need to, in order to get a stable results, you need to tweak a bit and train your model better with the different images and sources. So let's go back to our talk presentation. So what we can learn from these experiments and from the overall knowledge. First of all, the main and most important thing is data. So properly prepared data will give you the best results. And it's hard to give a model a lot of good data because you need to work with it. You need to create it. You cannot just have it from somewhere. Obviously, there are models, and obviously there are data banks and with images and so on, which you can use. You can download a lot of photos of dices, but you need to process it. You need to annotate it. And in order to annotate them, you want to make this process of annotation as automated as possible. Create custom scripts, which will help you and which will reduce the amount of work you need to do. Validate those annotations. Scripts are not perfect, and they work better on some specific samples, on the contrast backgrounds, on the white dices, and so on the good contrast images. But they are not perfect, and they will give you faulty information. You need to have a tool to validate it and to correct it as visual as possible, as fast as possible, as useful as possible. And remember that you can always retrain or add additional training to your model. If it's not successful right now, you should not throw it to the basket. It's not wasted. You can train more and improve the results. And for your application, it is useful to have settings of different confidence coefficients that you can change in order to improve the output feed. So kernel vision in its entirety gives you a lot of instruments to do a lot of applications from the list we mentioned, and even much more on device, and to enable your applications with this incredible functionality. And you need, as it was previously, you needed to call the server and query the server for results to process and so on and so on. Now with kernel vision, you can do it on device, and you can enable any of your application with the functionality of the best technology leaders. For example, you can create an application that blurs background like it does in Zoom, but you do not need to invest a lot of money and resources because you already have a vision framework which allows you to capture the stream and to identify the, for example, person object and to blur the background. So that's all, folks, from my side. Thank you for your attention. And here's the QR code and link to the information and useful links where you can find the raw dataset for this presentation I used, and many more videos from Apple and WWDC about the kernel vision. Thank you.
Thank you very much for your talk, Kostiantyn. It was lovely. And by the way, very nice design of your presentation. Have you done it by yourself?
Yeah, except the first and last slides.
Okay, but it was perfect. I invite you to the discussion table together with our participants. So please join Kostiantyn in the discussion table.